Hello, Physics 1. Welcome back to part 2 of Tuesday's lecture. So, moving on with another example where we're going to look at extended versus point particle model systems. So, you are playing with a yo-yo with a mass of 0.07 kilograms. I'm going to highlight important things in this question. It is attached to a low mass string. That indicates you can neglect the mast. So you pull up with a force of 0.4 newtons. So you are applying this force. And your hand moves, delta R hand is equal to 0.25 meters. During this time, the mass falls delta R yo-yo 0.45 meters. Taking string off the axle with it. Just like you would expect a yo-yo to do. Okay, so we want to go after the change of translational kinetic energy and the change of rotational kinetic energy. So we know yo-yos translate when they go up and down, and they rotate. Okay, so for K translational, we need the point particle model. So in this case, our system is the point with mass 0.07 kilograms, and the surroundings are the earth and hand. So in the initial state, you have some initial translational kinetic energy, and in the final state, you have the final translational kinetic energy. Okay, so, because yo-yos typically, when you get to that point, they're already in motion. Okay, so looking at this, you're going to have 0.4 newtons from the hand, and then you're going to have mg going down. So that's 0.07 kilograms times 9.8 newtons per kilogram. And we know that it moves delta R yo-yo .45 meters. So we know that there is some non-zero displacement. Okay, so taking what we know, let's apply the energy principle to our point particle model. So we have the change of translational kinetic energy is equal to F net y delta y of the center of mass. The change of kinetic translational energy is equal to 0.4 newtons minus 0.07 kilograms times 9.8 newtons per kilogram. And both of these forces are applied the entire time because they all act in the center of mass over that distance of minus 0.45 meters. By the way, the distance your hand moved up, which we talked about at the very beginning, so your hand was displaced a quarter of a meter, that's irrelevant. We don't need that information for the point particle model. It's important later though. So, the change of translational kinetic energy is equal to 0.291 joules. Okay, that's important. Let's put a red box around it. Save it for later. All right, so to go after the change of rotational kinetic energy, we need the extended system. Go, extended, go, go, extended. So our system is the yo-yo and the string. Our surroundings is the earth and hand. Our initial state, here we have some, we know it was spinning because we know how yo-yos work. So it has some translational initial and some rotational initial. And I hope you've been noting that when you do the extended system, the translational aspect of it is a part of it. It's just not the whole of it. So we would have some translational final and some rotational final. Okay, so we need a different diagram. Here is our yo-yo. And it's going to be displaced delta y over a negative 0.45, so please note the negative sign that was up here. And we also, as a part of the system, we've got the hand. So the hand is displaced some delta y, 0.25 meters. And then I'm gonna, so this is basically showing displacement. I'm gonna do a different diagram for the forces. So once again, we've got mg on the mass, and then we've got our string. And then we have F normal equals 0.4 newtons from, not normal, it's F hand, from the hand. Okay. So moving on. To the energy principle. So the change in energy of the system is equal to the work from the hand plus the work done on it by the earth. Both of these are acting over a non-zero displacement. So we have the change of translational kinetic energy plus the change of rotational kinetic energy for delta E system is equal to 0.4 newtons times 0.25 meters 0.07 kilograms times 9.8 newtons per kilogram over that minus 0.45 displacement. And so what we have is that delta K translational plus delta K rotational is equal to 0.4087 joules. Now, aside, we know that the change of translational kinetic energy is equal to 0.291 joules. So using that, we have 0.291 joules plus the change of kinetic energy rotational is equal to 0.4087 joules. Therefore, the change of rotational kinetic energy is equal to 0.118 joules. And there you go. Once again, we see another application that in order for us to go after the complete answer, we needed both that extended system and that point particle system. And the key difference is the extended system brought into it the displacement of the hand. Okay, another example. So really the best way to do these types of problems is to just do example after example after example. So we have a woman on roller skates. So for those of you who don't know, I used to do artistic roller skating. So like what you do on ice skates, I used to do on roller skates. And yes, it requires more strength because you have to combat the friction of the floor and the heavier weight of roller skates over ice skates. So she stands at rest in front of a wall with her hand on it. She pushes the wall causing herself to roll backwards. So there she is on skates, in contact. Apparently has grown a third arm, and then we're not going to include this, but eventually she'll lose contact with the wall. So we are looking from next to the wall into the moment just before she leaves contact. Okay. So once again, we're going to look at the extended model and the point model for this system. Starting with the point, so breast in motion. So we'll draw our diagram. So we've got the force from the floor, the force mg, the normal force from the wall. There they are, all acting on her center of mass. Our system is a point of mass m, which is the woman's mass. The surroundings, wall, floor, earth. All in all, we're just bricks in the wall. And the initial state is at rest. Final state, unknown V. So she's got some speed at the end. We don't know what it is. Okay, so energy principle time. So the change of translational kinetic energy is equal to work. The change of translational kinetic energy is equal to the force applied over that distance that she moves. 1/2 mv squared minus 0, because she started at rest, is equal to FD. V is equal to 2 FD over M. Wrap it up and put a bow on it. We are done with the point particle model. All right, moving on to the extended system. So our system is the skater, our surroundings. We have the wall, the floor, and the earth. The initial state, at rest, and the final state, speed. V is equal to 2FD over M. And we know that there's an internal energy change because she had to heat up and use some chemical energy. All right, so the change in energy of the system is still equal to work. So let's start back at basics. And let's draw one of those stellar pictures. So here she is on her skates with her arm and that normal force from the wall and that force from the floor, just acting on the wheels there, and that good old mg going down. All acting on different places. So remember, we stopped this interaction before her hand left the wall. So that way that normal wall is going to be there the whole time. Okay, so let's set up the energy principle and expand it out. So we've got the change of kinetic energy translational plus the change of internal. We don't really have rotation. This is going to be equal to force over 0 displacement. What? Why? Well, let's look at this. These are perpendicular to motion, therefore no work. And this is over 0 displacement. No displacement. No work. There you go. No work with the extended model. Okay, so we know from our previous point particle model that the change of kinetic energy translational is equal to the force times the distance that that center of mass moves over this interaction. So we have FD plus delta E internal is equal to 0. So therefore, delta E internal is equal to minus FD. And this has decreased chemical energy embedded, as well as some increase in heat. All right, so this is where we wrap up Chapter 9. We don't do the modeling of friction. If you're very interested in that, you can do complex models of friction if you take engineering-related courses. We do have an engineering program in conjunction with Washington University at Northwestern, if that's something you're interested in. It's still an interesting section, but we don't cover it in this semester. So just some final thoughts. So the energy principle is fundamental. And part of the analysis involves clever system choices. To maximize information. All right, so that wraps up part 2 of Tuesday's lecture. I will see you for Wednesday's lecture where we will begin Chapter 10 on collisions. And I know that's what you came here for.